Welcome to Empowered Learning. This video will be about the introduction to polynomial approximations. Specifically speaking, what we are going to talk about is the motivation and the reason behind why in, let's say, a second year calculus course, you talk about things such as sequences, series, and you have all these hosts of tests to know whether a particular sequence and or series will converge or not. So the main idea is that a lot of times we're asked to evaluate the integral of some function, and that function does not have what we call an elementary function antiderivative, meaning that we cannot express the antiderivative of that function in terms of the well-known functions that we know, like logarithms, exponentials, polynomials, rational functions, radical functions, so on and so forth. Okay. So with that being said, we are kind of at a loss for how to find the antiderivative of those types of functions unless we do numerical integration, such as Raymond sums, Simpson's rule, trapezoid rule, where you're basically just using the area of shapes that you know, or the area on the curve of a parabola in sense of, I guess, in the case of Simpson's rule, to be able to estimate the area under the curve. Okay. And of course, all this comes about when you're kind of in a situation where you have to evaluate the antiderivative for a particular function, and all the integration techniques that you learn in a second year calculus course, except for, let's say, numerical integration, does not work for you. Okay. So in this sense, we need to have another way to be able to express the antiderivative of the function that really doesn't have a nice clean way for you to express the antiderivative of it. And so it turns out that polynomial functions is the way to go, because polynomial functions are essentially sort of like our, I like to call it the Plato function. We could lay it on anything and the right polynomial will give us that equivalent or good approximation of what that particular function is over a range of x values. So that's really kind of the idea here. The other reason for that is because, of course, if you've studied calculus, one of the things that you know is how to be able to take the antiderivative of a power function, which we know a polynomial is just a sum of power functions. And of course, that's real simple. So if I had, let's say, x raised to the n, and I wanted to take the most general antiderivative of that, we know that's just going to be x raised to the n plus 1 divided by the same plus some integration constant. And so if we can get our functions that do not have elementary function antiderivatives at least at a good approximate form of some polynomial, then we can have a fairly close assessment of what its antiderivative is. Of course, it won't always be exact, but it'll at least give us a good estimate. And so that is kind of the motivation for that particular subject or concepts in a second year calculus course. And so here what we are going to do is to try to see in a very simple way how that comes about. Okay. So first, why do we use polynomial approximations? Well, before we had computers and electronic calculators and such, many of the math and science books that we had would actually have trigonometric, logarithmic, and exponential function values stored in the back of it in tables. So like, for instance, if I wanted to know what sine of 1 degree is, or sine of pi over 15 radians would be, that would actually be in a table. Okay. If I wanted to know what e raised to the -2 is, that would be in a table. But now that we have calculators, we could actually store the polynomial approximation for each of these types of functions in a calculator in its memory, and thus all we have to do is just say, hey, let's call on this particular polynomial, plug in this particular x value, and it'll do all the number crunching for us to get the answer. And so that saves a lot of time, also saves a lot of memory, and thus a lot of cost as well, because we can store a lot of things in a very small space. Okay. Now, where does this motivation actually come from? Well, it comes from curve-fitting approximations of functions. So one of the things that we see all the time, we may not know that we're seeing it, but we do, is that whenever we have situations where we have to sort of approximate or give an idea of the trend of something or how something is acting or behaving, a lot of times we use graphs to do it. So for example, whenever you'll hear somebody on the news or you're reading a report or let's say an article online or whatnot, and they'll say something like, this particular thing is growing at an exponential rate, or this thing is growing by 2 to 3% per year. Another way of saying the same thing is growing exponentially. Well, we know that if we were actually to track the actual change or behavior in the thing that we're measuring, it's probably not going to act just like an exponential function, but its general behavior overall acts like one. So what we do is we will approximate what that would look like. So to kind of make my point here, let's say we had some data and those data points kind of look like what I'm doing here. Okay. Now, in general, we know that these data points here do not represent an exponential function, but we see that the general trend is going up like this, which does look exponential. Okay. And so that's where the whole thing with curve fitting comes in. Now, the reason why we say, well, hey, polynomial approximation kind of comes from curve fitting. Well, what if we had data that was, really, really tight as far as how it grows exponentially? Okay. Well, our question is if I wanted to express that as a polynomial, how could I do that? Okay. And so that's where the whole thing of polynomial approximations for functions actually comes into play. Now, the most well-known way of being able to approximate a function is linearly. And so for those of you that are studying, first year or second year calculus, you've probably seen this particular function or this particular formula before. And basically what we do is we take a function and its first derivative at some particular x value, and what we say is that we are linearly approximating our function f of x centered about some value x equals a. And I'm saying x equals a because it is going to be an x value. Okay. Now, of course, curve fitting approximations, and thus is going to turn out that polynomial approximations can be done as a constant function, a linear function, a quadratic function, cubic function, quartic function, so on and so forth. Okay. And what I mean by a constant function, it can be approximated by a horizontal line or a polynomial of degree 0. Okay. A linear function, it'll be a line again, but its slope won't be 0, so it'll probably look like this or like this, and that would be of degree 1 for the polynomial. For quadratic, it would look like a parabola, either like this or like this in general, and it will be of degree 2. Of course, cubic will either look like a function that looks like this or like this, be of degree 3. Quartic of degree 4 looks a lot like a degree 2, just rises and falls faster, so on and so forth. Okay. So why use polynomial versus other functions? So I mentioned this before. The polynomial is sort of like our free form, or as I like to call it, the Plato function of mathematics. So because of that, it can actually take on the shape of any other function that we have over a range of x values. And so that part of over a range of x values is important because that's the part where we have to figure out, well, is a series going to converge upon these values or not? So in your second year calculus course, when you study that sort of thing, trying to figure out what that range of x values is for where your polynomial function can approximate the function that you're looking to approximate is something of importance. And so that's the other piece to the puzzle. Now, this video will actually go over the first part of that, which is just finding a way to express the polynomial itself. And of course, in other videos that I'll make, when we start talking about different types of tests for these series that will represent these functions, we'll get into what's called region of convergence and all that good stuff to figure out, well, yeah, I can represent this particular function approximately by this polynomial, but over what range of x values could I possibly do that for? Okay. Now, the reason why I have this acronym here, FTOA, which is Fundamental Theorem of Algebra, is because one of the basic facts that comes out because of the Fundamental Theorem of Algebra is this whole thing that a polynomial could basically represent just about any function over a given range of x values. Okay. All right, so what we're going to do next is to sort of take a step back here for a second and see, well, how does this all come into play in the first place? And we're going to start back with first year calculus concepts of the derivative. And we're going to talk about the definition of derivative, meaning limit of difference quotient. We're going to take that concept and sort of build it to where we will eventually get into talking about linearization of functions. So you'll see how we actually get this particular formula to approximate a function linearly. And then after that, you'll see what does it look like whenever we want to approximate something quadratically or cubically or quartically. Okay, so we'll start that next. All right, so let's recall here that whenever we talk about the derivative of a function evaluated at a particular x value, and we're just going to call that a, one of the ways that we could express that is limit of the difference quotient. And this is one form of limit of the difference quotient here. Another form is this way. Now, the one thing that we know that's in common here, and I'm just going to say it like this. So if we were to let h, which means the same thing as x minus a, because remember, h is just the difference in the x values as they move closer and closer together to each other. X minus a is the same thing, the difference in between some random x value here and a fixed reference x value a. And of course, we know that we can always express that as delta x or a change in x. So if we had this case here, then we know as delta x approaches dx, and what dx is here is called a differential for x. So you can think of it as the smallest possible theoretical change in an x value that's quantifiable. So if, and of course this is happening as this approaches 0. So as the change in x values approaches 0, this is actually going to be going towards dx, because theoretically speaking, if the change in x could equal 0, then dx would actually be what its result would be. Okay. So then we know here that delta x will be approaching this theoretical value of dx as h approaches 0. Okay. And so now you see why I was saying here that delta x equals 0, because delta x and h are the same thing. Now, if that's the case, then what we could do is we could drop this whole limit notation here and actually express our derivative of this function at x equals a like what I am writing here. So basically, the h part, I'm saying, all right, well, when it gets to theoretically delta x being 0, I can just replace h with dx. So that's pretty much all that I'm writing here. Okay. Now, if I was to take this and rearrange this particular equation around, then I would see here I would have f prime of a times dx, and this would be the same as f of a plus dx here minus f of a. And if I kept on going here and I solved for f of a plus dx, then I would essentially just have f of a plus f prime of a times dx. And so if you're looking at this, you're saying, hey, this looks kind of similar to the linearization of a function at some value x equals a. And you're exactly right. Okay. Now the idea here is that notice that f of a plus dx is going to be a y value that is very close to f of a. Okay. And so because of this, we say that f of a is not exact, but it's a good approximation to what we see here. Okay. And I'm going to write this way. So it's going to be a good approximation to what f of a plus delta x actually is, which is going to be all this business here. Okay. And now, if I wanted to do this, remember that our delta x is equal to x minus a. So I really could come here and replace this delta x with just x minus a. Okay. So I'm going to go ahead and do that now. And so in doing that, you see that f of a can be approximated by the linear approximation of some function at x equals a. So this is where that linear approximation here comes into play in being able to estimate what is going to be our function at some specific value x equals a. Now, the thing that I want to kind of illuminate to you here is that we've talked about linear approximation, but we could talk about constant approximation. We could talk about quadratic approximation, cubic approximation, so on and so forth. Okay, so since we've already started with linear approximation, then if we wanted to represent f of a with a quadratic approximation, then it follows here that I would need a quadratic type function. So here I could say that f of a with a quadratic type of approximation could be something like this. And all I'm doing here is just following the pattern that I see here. So it could possibly be something like this. Okay. Now, in general, if we were to let, let's say, if we were to let this f of a be c sub 0, let this be c sub 1, let the second derivative here, this be c sub 2, then of course this would just look like c sub 0 plus c sub 1 times x minus a plus c sub 2 x minus a squared. Okay. Now, if I wanted a cubic approximation, then of course I would add another term to this, right? So my f of a now, in general, will look like c sub 0 plus c sub 1 times x minus a plus c sub 2 x minus a squared plus c sub 3 x minus a cubed. Okay. And of course, if I went on and I wanted to do Quartic approximation, I would add another term to that. And eventually, let's say if I wanted to do what we call an nth degree, meaning a polynomial of degree n calculation or approximation for this, this would basically be c sub 0 plus c sub 1 x minus a plus c sub 2 x minus a squared, and we just keep on going, and eventually we'll have c sub n times x raised to the a, x minus a raised to the n. Okay. So our goal here is to sort of force whatever function that we are going to be working with to sort of fit the profile of a parabola, like, well, not parabola, but a polynomial of what we are seeing here. And so for the rest of this video, our aim is going to be in doing an example to actually showcase them. Okay. So for this example that we want to do, we want to consider the function e raised to the negative 2x. And so what we want to do is basically find a polynomial that's going to approximate this particular function, and we're going to center it about a equals 0. So graphically, what that means here, and I'll just go ahead and sketch a quick graph so that we can kind of see what we're talking about. So graphically, let's say that we have some function e raised to the negative 2x, and of course that'll act like this. And we say that we want to center this approximation about a equals 0. Okay. So what that means here is we're basically going to center it about an x value of 0 and just kind of work with it from there. Okay. So here, let's say this is where that point is. And of course, we know that e raised to the negative 2 times 0 in the exponent would just be e raised to the 0. E raised to 0 is 1. Okay. So what we are essentially doing here is trying to say, hey, if this is going to be the center about where we do this approximation, let's try to get a polynomial that's going to lay on top of this particular function here, or lay beside it as close as it can when we do that. Now, if we had a linear approximation, of course, the line that we would have would look something like this, and these values that are very, very close to x equals 0, kind of on this interval here, from this x value to this one would be a very good approximation. That line would approximate what e raised to the negative 2x would look like really good. Okay. Now, of course, if we got a little further out, like around here, then of course the approximation is not as good. If we came out here, then of course again the approximation is not as good. So with the linear approximation, we know that we have to kind of stay close to this x value of a is equal to 0 in order to make everything work. Our goal is to see, well, what happens whenever we have a polynomial essentially of nth degree, so that we can have more of this line per se lie closer to what this function will look like. And of course, to be able to do that, we're going to have to add more terms to our linear approximation. All right, so let's go ahead and get started with that. So I'm going to erase this drawing here, and then we'll start kind of putting together what this polynomial should look like. Okay, so first thing here is we know from what we talked about earlier. Let me go back to this. You see how we had the quadratic approximation, cubic approximation, and of course nth degree approximation. So we are going to start off with this assumption here, okay? So in general, I'm going to say let f of x equal to c sub 0 plus c sub 1 times x minus a plus c sub 2 x minus a squared plus c sub 3 x minus a cubed, of course, dot, 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 and we'll get to having c sub n x minus a raised to the n, okay? And so basically we're saying let f of x be equal to some nth degree polynomial here, okay? And really this is just going to be an approximation, but we're going to try to do as much as we can to make it as exact as possible. So if we're looking here, we already know that a is going to be 0, so that's going to make life easy for us. We also already know that, of course, as we go from quadratic to cubic to quartic, the value of n is going to go up. So the only thing that we don't know is what our coefficients are: c sub 0, c sub 1, c sub 2, c sub 3, so on and so forth, okay? And so that is what we need to find, because if we can find those, then we'll have a polynomial that will characterize what this e raised to the minus 2x would be. So first, let's find c sub 0, okay? So to do that, of course, we'll just let x equals a here. Because again, we want to figure out what this particular function is going to approximate, but of course everything is going to be centered about x equals a. So if we do that, then here, if I do c sub 0 plus c sub 1, a minus a plus c sub 2, a minus a squared plus c sub 3, a minus a cubed plus dot, 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 and of course c sub n a minus a raised to the n. Now, of course, you've probably already noticed here that all of these other terms, other than the first one, are all going to go to 0 here, okay? And so all we have left is this f of a is equal to c sub 0. So here we have f of a, which is equal to c sub 0, okay? Now, we also know, so I'm going to say but, we know that f of a is also equal to e raised to the minus 2a. Of course, we're plugging in a for x there. And that is going to imply that if a is 0, that this is just going to be e raised to the negative 2 times 0 here, which will just be 1. Okay? So, in short here, the main things that we want to illuminate is that f of a is going to be c sub 0. we also know that f of 0 is going to be equal to 1. All right, so we have found what c sub 0 is in terms of a, or f of a, and we've also figured out what c sub 0 is just on its own. Okay, and let me go ahead and make sure that I notate that there. The main things that we want here is what the coefficient value actually is, and we want to see what that coefficient value is, how we would get it in terms of f of a. So next we are going to figure out what is c sub 1. Okay, so find c sub 1. Now, in order to do this, notice that to find c sub 0, it was very easy to do because it was this first term here. And notice how all these other terms had an x minus a in it. And if I could plug in x to be a, it would basically cancel all those terms out. Well, to get this c sub 1 by itself here, what I'm going to have to do is take the derivative of f of x so that I can have c sub 1 here by itself. Okay, so that's going to be the strategy here. So we're going to find f prime of x to get c1. Okay, so if we go up here, we know that if we take the derivative of this function, of course the derivative of any constant is 0. So we're not going to write that. The derivative, so we will write c1 though, and the derivative of x minus a, where a is a constant, is just going to be 1. So this will just be just c1 for the first term. For the second term, we would have c2, but since this is x minus a squared, we would use the power rule and say that's going to be 2 times c2 times x minus a, and then of course if we took the derivative of x minus a, because we would have to do the chain rule, of course that would just be 1. So there's no point in writing that, so we'll just say that it's just going to be 2 times c2 times x minus a. So in the next term it'll be same thing, so we'll have 3 times c3 times x minus a. If we did another term, it will be 4 times c4 x minus a. And of course, this will be squared here, and this will be cubed, because here we know that we would say 3 times c3, and then we would subtract 1 from this exponent here. Okay? And of course, we keep on going. Once we got to the nth term, we would have n times c sub n times x minus a, and all that raised to the n minus 1. So once we have that, then of course, if we were to plug in a into this first derivative, then just like before, all the other terms are going to go to 0 because they have x minus a's in them, and all we would have left is c1. Okay. Now, remember that f prime of a, if we just looked at our function, and I'm going to circle this just so that you know where to focus. If this is f of a, then f prime of a would actually be just e raised to the minus 2a times a negative 2 because of the chain rule. So this will be a negative 2e to the negative 2a. Okay. So now that we have that, we know that a is going to be 0. So therefore, f prime of 0 here, if we look at it, it's just going to be a negative 2 times e raised to the negative 2 times 0. And of course, e raised to 0 is 1. So this final answer here ends up being a negative 2. Okay? And of course, that is the same as what C1 would be, because again, what we're trying to do is approximate, well, we're trying to find out what these coefficients would be. Okay? And of course, we said that A was going to be equal to 0 here. So the main thing that we want to pull from this is that f prime of A is equal to C1, and that C1 is equal to negative 2. Okay? So that's the main thing, and I'll just go ahead and rewrite it here. So we got this, and of course, C1 is equal to negative 2. All right, so we're going to do this at least 2 more times so that we can kind of see what the pattern is going to be. And then from that, we'll be able to put things together and show you how we can actually form this polynomial that's going to approximate our function e raised to the negative 2x. All right, so now we are going to find our constant C2. Okay, and we had to find the first derivative to get C1, so we're going to need to find the second derivative to get C2. Okay, so again, we'll take the derivative of the derivative here, and of course, the derivative of any constant is 0. Derivative of the second term here will just be 2 times C2. And then next term here will be 3 times 2, which would be 6 C3 x minus a, plus next term will be 3 times 4, which is 12, times C4 x minus a squared. And then of course, we could keep on going here. So we're going to make this simple. And so this will be n times n minus 1 times c sub n x minus a raised to the n minus 2. And so from here, we could simply just plug in a for x. And of course, all those terms except for the first will end up going to 0. So here we see what C2 could be. So C2 is just going to be f double prime of a divided by 2. Okay, so that is what that would look like in terms of f of a. We also know that f double prime of a, here if we go back and look here, is going to be the derivative of what I'm circling here. So if we look at that, we know, kind of following the pattern here, we can ignore the negative 2. The derivative of e raised to the minus 2a is just going to be a negative 2 e to the negative 2a, which means this is essentially just going to be 4 times e raised to the minus 2a. And thus this means that f double prime of 0, because remember a is 0, is just going to be equal to 4 times e raised to all this business here, which is just 4 at the end of the day. So with all that being said here, the main things that we want to highlight again is that C2 is equal to second derivative of our function f over 2 and we know that here C2 I forgot to write this here, so I'll go ahead and write it, that this f prime of 0 here is equal to 2 times C2. And so what this will tell us, that of course we divide 2 on both sides here, is that C2 is equal to 2 there. So we know that. And let's make that look a little better. And this will be f double prime of A. So again, we have C sub 2 written in terms of f of A, and we have what the actual value of C sub 2 would be in this particular example. All right, so let's go ahead and do this again for C3, and then after that we should be able to see enough. Well, let's do it for C3 and C4, and then we should have enough there to be able to come up with a pattern. All right, so moving on to finding the coefficient C3, I've gone ahead and actually wrote out what C3 and C4 are so that we can kind of go through this a little bit faster. So here, again, same process. We want to take the third derivative, which will be the the derivative of the second derivative here. Of course, we get this 6C3 plus 24 A sub 4 x minus A, so on and so forth. We know that whenever we plug in A into it, all the terms after the first will go to 0, and of course we'll be left with that first term. And of course, if we divide both sides by 6, we'll get what C3 is in terms of f of A. Specifically speaking, the third derivative of f of A divided by 6. But of course, we also know that the third derivative of f evaluated at A, if we kind of look at what we have here, this is f prime of A. So if we take the derivative of what we have here, that will give us the negative 8e raised to the negative 2a. And of course, if we explicitly plug in a equals 0, then we see that the third derivative is going to equal a negative 8, but that also has to be equal to this 6 times C3. So that means that our C sub 3 is going to be negative 4/3 once we're done. And of course, we have C3 now expressed in terms of f of A, as well as the actual number there. And let's see, I put second derivative on this, and it actually needs to be third. So let me go ahead and correct that. So let's go ahead and take care of that right fast. So 1, 2, 3 ticky marks. All right. And so now we'll use the info from finding C3 to figure out what C4 is. Kind of the same thing. We take the derivative of the third derivative to get the fourth derivative. Of course, this is the term that we're really concerned about, that first one. We know that all the stuff that comes after that is just going to eventually go to 0 whenever we plug in A into it. Divide both sides by 24, and we get A sub 4 in terms of, and really that should be C sub 4. I don't know why I have A there, so let me change that as well here. All right, so I went and changed those A's now to be C's for the coefficients. So again, once we have our fourth derivative, we know once we plug in A, all the terms except for the first will go to 0. And of course, we'll take what C4 is, which is the fourth derivative evaluated at A divided by 24. But we also remember that our fourth derivative could also be the derivative of the third derivative with A plugged in. And of course, that ends up just being 16 times e raised to the minus 2a. If you explicitly plug in A is 0 here, then we'll get that basically 16 is equal to 24 times C4, which after you solve for C4 is going to be 2/3. And we again, know what c sub 4 is in terms of f of a. It's just going to be the fourth derivative of the function evaluated at a divided by 24, and c sub 4 is going to be 2/3. So with this being said here, we notice that there's a pattern going on. Okay, so we'll kind of go back to where we started here. Now, I purposely wrote this in terms of f of a as well as what the actual value is, so that we can kind of see both things at the same time. So in terms of our coefficients being in terms of f of a, of course, we just have c sub 0 is f of a. But of course, c sub 1 is going to be f prime of a. C sub 2 is the second derivative of f evaluated at a, or f double prime of a divided by 2. C sub 3 is third derivative of function a divided by 6. And fourth derivative is and c sub 4 is the fourth derivative of the function evaluated a divided by 24. Okay, so if we look at that all together, this is kind of what it looks like. And so we notice that in the denominator here, of course, these first two we don't have anything, but we can assume that those are 1. And we notice that the last three, 2, 6, and 24, are sort of following the pattern of a factorial. Okay, and if you're not familiar with what a factorial is, just for example here, we know that 3 factorial is just going to be 3 times 2 times 1, which will be 6. So that's a quick example of a factorial. So knowing that, we see that it's following that pattern, and we could easily see that it's following that pattern of the factorial if we go back to the top here and notice that for the c sub 4, notice that our last term here looked like this. And of course, that's letting us know that our nth term of the polynomial is going to be proportional to whatever n factorial is. Okay, so needless to say, what that turns out being is that if we look at our factorial as a recursive sequence where the first 2 terms are defined, mainly 0 factorial and 1 factorial, if we predefine those as 1, and then of course for any other integer values, not integer, but natural number value of n, mainly when it's 2, 3, 4, 5, 6, 7, 8, 9, whatever, whatever that value is factorial is just going to be that amount going down a natural number value all the way until you get to 1. Then of course we could express our coefficients as the nth derivative of f evaluated at whatever a is divided by n factorial. And this formula here lets us know what our coefficients would be no matter where we are actually centering our function f of x around. Okay, so right now we're doing it at a equals 0, but we could do it at a equals 1, a equals 5, a equals 7, a equals 2/3, whatever we wanted, of course, as long as that value of a is in the domain of the function. And since e raised to the negative 2x, its domain is all real numbers, we don't really have that issue there. Okay, so now that we have all that in play here, we could actually see, well, how are we going to write out our polynomials now? If we want, well, how are we going to approximate our function if we wrote it out as a constant polynomial, a linear polynomial, a quadratic polynomial, a cubic polynomial, so on and so forth. Okay. All right, so for our constant function approximation, we know here that our function f of x here is just going to be approximated to whatever c sub 0 is, which in this case is 1. And of course we know that because if we go back and look at what we had to begin with, we saw that c sub 0 is 1. Okay. Now that also means that, of course, c sub 1 is negative 2. And we're going to use that to be able to approximate our it linearly. Okay. So if we want to do a linear approximation, let's make this look a little better here. So linear approximation. Then our function would be approximately CO plus C1 times X minus A. And according to what we have here, we know that A is 0. So this would just be 1 minus 2x. So this linear function would approximate our function e to the x roughly. So if we wanted to do a quadratic approximation, then here we would have f of x is approximately equal to c sub 0 plus c sub 1 times x minus a plus c sub 2 x minus a squared. And of course, plugging in everything, of course, the first two terms will be a 1 minus 2x again. And if we go back and see what c sub 2 was, it is a positive 2. So since it is a positive 2, the next term here is just going to be plus 2x squared. And that would be our quadratic approximation of what our function e raised to the negative 2x would be. If we wanted to do a cubic approximation, then of course we would add one more term to that. I'll go ahead and write it out here. So, of course, this would be equal to 1 minus 2x plus 2x squared. So that's the first three terms. And if we go back and see what C3 is, we know that C3 was a negative 4/3. So here this would be a negative 4/3 x cubed. Okay. And then, of course, if we wanted a quartic approximation, then this would be f of x. And of course, we would add one more term to that. Kind of see how this is working here. Because essentially all we're doing here at this point is just following the pattern. And this would be equal to 1 minus 2x plus 2x squared minus 4/3 x cubed. And this would be plus 2/3 x to the 4th because we know that C4 here was 2/3. And of course, just for fun, we could do one more here, Quintic approximation. That is a 5th degree polynomial. And I won't write out all the the basic stuff here for it. I'll just write what the answer is. And so this will be f of x is equal to 1 minus 2x plus 2x squared minus 4/3 x cubed plus 2/3 x to the 4th. Last term here will be plus 4 over 15 x to the 5th. And so you see, of course, as we know more coefficients, we can, of course, get more terms. And what this ultimately will mean is that we will have a better approximation of what this function e raised to the negative 2x actually is. All right, so in general here, if we wanted to get an nth degree polynomial approximation, so we'll just say nth degree polynomial approximation here, then what ends up happening is, of course, our function f of x can be approximated by f of 0, and I'm doing it specifically for this case here. F of 0 plus f prime of 0 times x plus f double prime of 0 divided by 2 x squared plus f triple prime of 0 divided by 6 x cubed. And of course, if we kept on doing the terms there, we would see that this last term will end up being the nth derivative evaluated at 0 divided by whatever n factorial is times x raised to the n. Okay? And so that means, of course, that for this function e raised to the negative 2x, that's going to be centered about a equals 0. We know that in general here, f of x could be expressed, of course this is what we're trying to do here, it could be expressed this way. And I'm going to write it in summation notation here. So I'm going to change my variable to k for the summation operator. And we can just essentially write it like this. Because of course every term that we're adding up is following the same profile of the whatever nth derivative evaluated at 0 divided by the same whatever factorial. And then of course it'll always be x raised to the whatever as well. So this is a very compact way of saying this. Now, if I wanted what e raised to the negative 2x would be exactly, if I wanted the polynomial that was going to mimic it exactly, even though, you know, from a practical standpoint it's not possible, but theoretically we could kind of force it to be that way. What we would have to do here is introduce limit. So we have to say the limit as n approaches infinity of all of this business here. And of course, n is going to be the degree of the polynomial. If that went to infinity, then we could just keep on writing out terms forever and ever and ever. And eventually, once we got to infinity, wherever that is, we would actually have a polynomial that would match up with e raised to the negative 2x exactly. Okay. Now, to close out this video, what we're going to do is actually see, well, what does that look like? Okay, so to do that, I have these graphs already done in Desmos. So you're going to see how each one is going to kind of compare, and you'll see as the degree of the polynomial gets higher, the more and more it lies along the actual curve of e to the x for certain x values. All right, so what I have here in Desmos is all of my functions. Of course, this first one here, f of x, is the actual function that we are trying to approximate as a polynomial. And of course, all the other following functions, except for this one here, this g of x one, is going to be functions that are going to approximate it based upon the degree of the polynomial that we use to do it. So of course, the grossest approximation is going to be the constant approximation. And of course, the only point it gets right on that is, of course, the y-intercept. So that makes sense. But here, let's see if we do the linear approximation. You see that it gets a little better. Okay, so I'm going to turn this one off. And you see how for these values, like in here, that line is lying along that function of e raised to the negative 2x pretty good. Okay. Now, of course, if we go do the parabolic or quadratic approximation, you see that it's a little bit better. Okay, so you see about from right here to about right here, all those points there are lying along the curve of the exponential pretty close. Okay. Of course, we move on and do a cubic approximation. We see that we have even more. So we see that these values from about here all the way up to about right here, very good approximation. All the way up to here is still close, but we're still off some. Okay. Now, of course, I'm going to skip this one, and I just did this because it kind of gave me the same color again as the original function, so I needed something to skip it. So now if we do the Quartic approximation, you see how for most of this curve here, it is laying along it pretty good. I would have to actually zoom in a lot to be able to see, where it kind of deviates some. So you see how I'm having to zoom in a whole lot here just to kind of see where it deviates. So that lets me know, hey, that's a pretty good approximation. Okay, so I'll go ahead and zoom out some more here. And so now, if I wanted to do and I'll go ahead and spread this out some here. Oops, got two of the same function here. So let me get rid of that. So here, this is the one that's the Quintic approximation. So this is the last one. So you see how it's very close to that. Of course, I could put more polynomial terms here, well, more polynomials of higher degree, and you'll see that it even gets closer and closer. And at this point, what will be happening is that, of course, on this side, as the polynomials get higher, there won't be that much difference there. But of course, the more terms we put here, the more this piece is going to start to lay on this bottom part of the e raised to the negative 2x function. Okay, and so this is sort of our workaround behind not being able to actually find, let's say, the antiderivative of a function that we can't find the antiderivative of using integration techniques in a first or second year calculus course. So this is the workaround around it. We just say, hey, we're going to approximate it as a polynomial, and of course, as long as we know for what x values will this polynomial approximation will converge on, meaning that for these x values, we can assume that if n is allowed to go to infinity, the x values are going to correspond to the exact y values of the original function. Okay, so whatever the polynomials y values end up being, it'll converge upon, or actually end up being the exact y values for the corresponding x value for the function that we're trying to approximate. So that's what that means. So hopefully, by seeing this done from beginning to end, you have a good idea of this whole concept of taking a function and and trying to approximate it using polynomials is all about. And of course, again, if you're following my video series here, eventually you're going to see us talk about Taylor polynomials, Maclaurin polynomials, binomial polynomials. And so the example that we actually did here was a Taylor polynomial centered about a equals 0, which is essentially a Maclaurin polynomial, or we call it a Maclaurin series, okay, and Taylor series. So you'll see more of this in the videos to come, and hopefully this helped. So take care.